So good afternoon, everybody. So I have a big pleasure to introduce Hundertmark from University of, now I forgot, Landau. Now it's these two universities together. And she, let me just introduce her that she did her PhD in the University of Komenska in Bratislava, special fellow. Then she moved as a postdoc first to the University of Hamburg, then to University of Mainz, and finally now she's professor at this Kaiserslautern University. And today she will talk about modeling of carotid arteries hemodynamics towards a CFD database for the stroke risk assessment. So we are looking forward.
Thank you very much. Thank you, Shaka, for inviting me to come to Prague and to give a lecture. Every time I'm very lucky to come back to Prague. I spend some time as a postdoc here at this institute here at the University in Prague. But this is a long time ago. So the work I will present today is. I'm doing something.
Could you just click on OK on the computer there?
On the computer? Okay.
Yeah.
So,
now
okay, let's back to the first. So I propose to stay here now. So this is a joint work with several groups, not only my group, we are a group of numerical simulation at the Institute of Mathematics, at the campus Landau of the new grounded University of Kaiserslautern London. It was grounded 2023, just joining through the marriage of these two places of Kaiserslautern and Koblenz Landau, which was split to Koblenz Landau. So, and the group of visualization and explorative data analysis from the University of Vienna is also collaborate on these works, and biomedical technology experts from the University of Stuttgart. It's kind of joint work which I present today, and we are part of a bigger project when we are responsible for numerical simulation on real carotid artery, patient-based carotid arteries. I said arteries because at the end we have produced a bigger database of hemodynamics of carotid artery with almost 200 patient cases. And now I would like to speak about it, how we did it and what we did. Okay, so carotid artery diseases, everybody knows these are very dangerous diseases causing almost 20% of all strokes. And therefore, the stroke risk assessment is very important. We are included, or we are collaborating on stroke risk assessment. Two things. Our approaches are database, so we are working with real data generation and data visualization, and the numerics groups are dealing with deriving risk predictors and so on. The work was done in the scope of the so-called NLGSA project. It is a project third party founded by BMBF, on English is German Federal Ministry of Science and Education. And you see also in this figure that we have both, we have CTA images, we have simulation, we have machine learning and so on. So what is our goal? Special goal is patient-based modeling and also visualization. Here you can see one head. It's not head, it's CTA scan or derived from CTA process. Kind of patient data. In green, you will see highlighted the carotid artery. And you can see already processed the 3D geometrical objects, not only of the artery, but also of the plaque. This white color regions is the heart plaque of a patient. And so this is the work of our visualization group, and numerical are dealing with kind of predictor, risk predictor or indicator of cardiovascular risk on these specific patient-specific or in this patient-specific cases. What does the acronym means? MLGS8 on German sounds something like machine learning against the strokes for stroke assessment. The data we simulate, they have been processed for some machine learning and for some classifiers of stroke risk. So I have couple of themes or topics today. Let's see which of them we will. I have like 60 minutes, so let's see what do we manage. But I start with the mathematical numerical model, a little bit about the numerical convergence, experimental convergence. Then I would like to say something about the modeling of these risk descriptors in patient-specific situation. Then about the compliance study, which is related to fluid structure interaction modeling. And then I would like to say something about our automated simulation flow, which we developed in order to generate a big database of hemodynamics data, and a couple of words on the data usage. So first we have a fluid structure interaction model. It's better when fluid structure interaction model. We have the fluid, compressible fluid equations with TF being stress tensor of the Newtonian, as well as in some cases we use some shear dependent generalized fluids in this TF, so viscosity dependent on the shear sometimes. But we have seen this has not so really big influence on our data. So then we left it. And we have coupled problem with the problem of the deformation of the vessel walls. V is the deformation vector for each point, not only on the surface, so on the vessel wall, but also inside in some thick structure domain. P of F is some deformation tensor, and S is the second pillar Kirchhoff tensor. And epsilon is shear, none is strain, except this is the strain. Yes. What we have this coupling condition, which are probably well known for everybody sitting here. We have continuity and continuity of the stresses here on the interface, or in our case on the inner side of the vessel wall. Okay, so classical model. At first, you can imagine that we have some linear elasticity, and in the next step, we try to generalize the model of deformation based on what we also have measured, or our partners from the biomedical technology. So we have measured data. The question of outflow boundary condition is important in this case. So what we have a vessel, carotid artery, patient base. You see this common carotid artery. ECA means internal carotid artery, interna, externa, which is also splitting in several daughter branches here. At the inflow, we took some typical flow rate of the carotid artery, which is kind of some wave behavior of the flow rate. And at the outflow, at first, as probably a lot of people doing hemodynamics or starting with hemodynamics, zero pressure, not zero pressure, zero scarcity outflow. And we took it at first for each of the outflow here, but this is not worked very well because of that. I will show the results, how does it work, and because therefore, we try to look for some different condition, outflow condition, because we do not obtain realistic behavior if the volume change behavior. So, so-called resistance boundary condition means that the pressure can be modeled as a product of the resistance and the flow rate. It comes from the electrical circuit analogy when you have current and voltage. So the resistance is the ratio between electrical current and voltage. And the same is applied here. So this is the total resistance of the whole artery system, which is here inside the carotid artery, can be obtained from the mean pressure and mean flow rate. Mean flow rate is some temporal mean of the inflow. It is the amount of the flow volume inside. Okay. Mean pressure can be obtained as a combination of diastolic and systolic pressure. All this information you can find in the literature, and also we discussed it with the physicians. So, and then it's nice, but okay. What is the pressure and what is the flow rate? It's known. And what is the resistance? Especially what are the resistances we have to prescribe to the outlets? This is the question. So one can take the analogy of the electrical circuit, and now when you have here you have parallel branches with the individual resistances, you can obtain the total resistance 1 over the total resistance. That's the sum of the one resistance. This is a very simple law of Ohm's law. So we have applied the same principle here. So the total, 1 over the total resistance is the sum of the reciprocal values of the resistances of internal and 3 or many external branches, which is the case by normal patients. Okay, but this is not enough. Now you have total resistance is known, but you do not know the these individual resistances. What you need. Okay. So how we can do what we can do as next? So the physicians say that the pressure or the resistance or the flow in the carotid artery and in this branch is somehow regulated by the intracranial arteries, such that the big amount of the flow rate, it is about 70%, is flowing into the internal and the rest in the external. About something, it can be patient individual, but these are this is the fraction. Okay, so from this information we can obtain now. So from this information, then you can distinguish between the external resistance and the internal resistance, which behaves with this proportion. Okay. Yes.
Can I ask what is known at the outlet? Is it pressure as well as the outlet velocity are known?
They are numerically computed. But pressure you can but in our case we prescribe the pressure. This is the boundary condition for the pressure. So we try
to based on the unknown outflow velocity. So
yes.
It is
somehow
like
implicit. Yes. It's implicit. Exactly. So yes, and now we know how to distinguish between internal and all this sum of external resistances. But still, you do not know which is the ratio between external 2, 1, and 3. And for this, we did something different. It is also in the sense of the Ohm's law. I mean that resistances in this external have been considered as a proportional to the outlet area. So you have the sum of the all outlets over the outlets. I say outlet of external, so 1 over resistance is exactly the same or the proper ratio here. Okay, so and that's all for the resistance boundary condition in the case that the vessel is rigid, so that you do not have fluid structure interaction. Yeah, but if you have fluid structure interaction, okay, so in the fluid structure interactions, what I didn't say that we have some outflow here, but the outflow surfaces are somehow closed, so they are not moving, okay? So we do the same. The principle of resistance boundary condition, okay, we need to prescribe pressure, okay, pressure resistance times flow rate, total flow rate, you have total resistance, and then you have the same relation between the total and the particular resistances. But now it is not the whole story, because now imagine that all the wall is moving. And when you have some movement, you have some velocity, you have some inflow or a flow into the walls. In the case of rigid artery, the resistance of the vessel wall was infinity. Okay, 1/infinity 0. So, but now the resistance is not an infinity somehow, and now we have to look at it. What is the resistance in that case? Okay, so but the resistance is a mean pressure. This is the pressure surface pressure of the surface, a mean of the surface, and the flow rate wall, which is the surface integral along on the gamma wall on the surface of the velocity. The velocity is time derivative of the derivative times normal vector, because a normal flow. Okay, so now we have another guy here. Good, but still, so this guy is just causing some inflammation, some volume change. But you have the same regulation through these arteries from the brain, that you have 30 and 70% splitting of the flow. And so for these resistances at the outflow, the same shall be valid. We denote all the sum of resistances outflow resistance, 1/outflow resistance, and we put the same condition that this outflow resistance should be split in the same ratio as before. It means, but then it means that for the internal, we have some resistance, which is this outlet resistance, which is the sum of all of them, or 0.7, and here, so 0.3. Okay, the only difference now is that here is not the total resistance thing, but only the outflow resistance. So you put some new term, but this term is not included in this computation. Okay, so and now we have all, and we have also resistance boundary condition in case of fluid structure regulation. And probably later on you will see the difference between implementing this boundary condition in fluid structure interaction case and implementing the zero boundary condition, the zero stress boundary condition, which is really not physical. Okay, why not physical? Because we have measurements. So now I come to some numerical stories, numerical convergence studies, which were necessary in order to publish the paper and so on. It's a little bit boring, but okay. We computed with console multiphysics and special what is called special kind of module, special model for fluid structure interaction, where the FSE is implemented in monolithic case of computing everything all together, high nonlinear system. Finite element methods, we use linear elements for fluid and pressure, and the quadratic elements for the deformation equation, tetrahedral mesh, two boundary layers, and so on. We performed a convergence study on fixed domain because of the amount of the computation. Because we have no regular mesh, so we cannot refine them. So refine each element highly increased computational cost and so on. Therefore, we took the strategy of doubling elements number. Okay, So we obtain non-coinciding mesh with different nodes for different meshes. And then we need to define some mesh decreasing factor AI, which is the relation between mesh sizes on each forthcoming meshes. This factor lies at 1.2, 1.3, okay? We computed reference solution with almost 9 million of elements, and we evaluated L2 weighted errors at maximal flow, which means systolic flow. Here you can observe the behavior of the error, so error decreasing independently on the mesh side in logarithmic scale, okay? And you also have this trend line for first and for the second order, so you see that we are lying somewhere close to the first order, but this is improving. The blue is the error for the velocity, and red is the error for the tau, which is the Walsh stress. So also some derived values, some derived. Okay, this is the definition of this L2 error, which is depicted on the figure. And now we are a little bit more details. So, okay, this was not clever to put this on this left corner, but so we assume that we have error behavior like in this manner. Okay, we have C times H to P, which is some means mesh size, and we're looking for this exponent P, which we call the exponential order of convergence. So if you look at this relation, if you look at this formula, so this is this P is the logarithmus by the basis of the I of this fraction of two errors. And in other words, this is nothing else, just finding difference. So the slope of the curves I presented before. Okay, so the slope of this right and blue curve is exactly this finite difference, kind of approximative, and this is exactly the exponential order of convergence P. Okay, and now you see we have six meshes, and on the 8th mesh, with almost 9 million, it was the reference solution. So this is the number of element size from 70,000 to almost 2 million something. Mesh size is decreasing, decrease of the error, and this EOC, when you compute the mean of them on the average, you obtain something more than 1 for the velocity and also for the Walsh stress. Okay, so clearly are not, we would expect second order, but for instance, at the inflow boundary condition, we have not continuity because we prescribe some temporal change velocity, which is this is constant on the outside. So at the boundary, we have some incontinuities. We do not expect really second order, but we are converging. And now here you can observe here the behavior of the solution with respect to the meshes. So at this left figure, you have the same mesh, fixed mesh. I don't know how many elements, but we change the number of boundary layers. For the convergence study, we just take 2 boundary layers and refine the mesh. But in this case, we took more boundary layers, and you see that the velocity, it is this line, equiline of the value of 60% of the maximal velocity, and you see that this behavior. So if we increase the boundary layer number, the velocity profile changed, okay? And the same behavior you can see here, you can observe here, but with different strategy. This is the velocity, 70% of the maximal velocity with mesh number 4, 6, and 8, like in the reference solution. You can see this velocity value, this isoline of velocity value on the reference solution is the same as the boundary, as the same for the solution with 8 boundary. What I want to say with that, The boundary layer, the resolution of boundary layer is very important for evaluating the Walsh stress, because Walsh stress includes the derivative of the velocity on the surface. So therefore, we have seen also these refinement strategies we converge to some case. Now I come to the second part, which is now the evaluating of the cardiovascular risk descriptors. And okay, what is made with that? These are surface indicators for detecting the complex pathological flow inside the artery. So what is inside the artery? We try to evaluate it on the surface. This is the Walsh stress. We are interested not only in its size, high, or for physician high Walsh stress bedside, no? But also the multidirectional behavior of Walsh stress. Makes sense to evaluate because this is somehow related to helical flow, to backflow, and so on. The oscillatory shear index needs the Walsh stress and integrated in time in order to evaluate the temporal changes and oscillation, temporal switching of the Walsh stress, but also of the direction of the Walsh stress. Okay, Walsh stress is normally aligned with the main flow. If it is not the case, it's bad for the hemodynamic. It can somehow mechanically damage, and it's higher risk in that case. Okay, so I will come later. Sorry, to this figure I will come later and explain what does it mean. But now I would like to explain what is the Walsh stress again in more details. So we have TF, which is the stress vector, stress acting on the wall. So you have seen, you have here some simplified figure. You have tangential plane and this stress vector, which is showing somewhere. Okay, this is stress of the fluid. Now, Walsh stress is nothing like a projection of this vector to the tangential plane. So this is this blue vector. Walsh stress is a vector valued size, okay, but normally, so here are the formulas for it. So you subtract the normal component of the vector T, okay, or you project is in some base vector, basic vector. So if you have T2 and T1 basic vector, which span the tangential plane, so you can write it like this. And normally the Walsh stress metric is considered as a norm of the size of this vector. We dealt with kind of orientation base, so-called longitudinal, or you can simply derive also in this manner the transversal Walsh stress. This is a Walsh stress component. This is a different component of this. This is one component of this Walsh stress vector. Okay, by component in a special direction. So again, now we have the same situation. We have tangential plane with basic vectors, and now we have a special vector TL, which we call longitudinal vector. This vector should be aligned with the main flow, or aligned with the artery. And now we project this TF vector, this stress vector, at first in the tangential plane, and then write this in different basic, in this longitudinal and transversal basic, okay, in different coordinate system. What is very important to find this TL vectors, this longitudinal vector, which is in some complex geometry, is not so easy as it looks like. So if you have cylindrical domains, everything clear, but now, and to find them automatically, okay, and for a huge database. Okay, so here now for the explanation, this figure. So this kind of zoom of bifurcation area of the carotid artery with this red color. Now, with this, look at first at this black color arrows. This is the Walsh stress vector, and this red color arrows. this is the longitudinal component of this Walsh stress. It means this is kind of this scalar. Okay. So you project this to the longitudinal and transversal, but we took just this longitudinal component. Okay, but okay, this is a scalar value as you see here, but we put this scalar value on a vector TL, which is the longitudinal vector, in order to have the impression. So you see that the Walsh stress somehow could align with longitudinal Walsh stress, and somehow a little bit different, but at least it has almost the same or the proper direction. Okay. Yes. The question is how to construct this TL vector field, this longitudinal vector field. And we borrowed the method of projection method of Montelucci and some authors of that. So they applied it for aorta. Here's the center line of aorta. And we have center line and center line tangent. So I mean, this is the tangent field aligned with the center line. What they did is extrapolated the center line tangent, and then they projected them to the surface, to the wall surface. Okay, this is what is written here. So this tangential vector field, which is aligned with the main flow, can be obtained from the center line. Therefore, the center line is very important. Patient-specific center line is very important for our modeling. It is aligned with center line tangent, and okay, and project this to the tangential flow. Okay, and some this is a known vector. Okay, and now you can compare the result. On the left side, you see the tangential vectors TL, okay, which are almost perfectly aligned with the flow which is from left to right side, and in this case on the right you have a, we call it generic tangential vector, what the software give you when you say, okay, please compute me a tangential vector based on some algorithm. So you see here that the tangential vector are not smoothly directed, and they are following some peaks or some, okay, so they are completely disaligned with the flow. So therefore unable to evaluate the longitudinal component of the Walsh stress. Okay, good. Now, how does it look like? Finally, on the left side, you have the Walsh stress, longitudinal Walsh stress, not the Walsh stress amplitude, not the size, but the longitudinal Walsh stress is the longitudinal component of the Walsh stress vector with generic tangent fields. So with this erratic behavioral tangent field, for instance, you can see here two zones where it is very problematic. You have a really this is discontinuous behavior of Walsh stress, which is not real, which is not correct. But okay, the bifurcation area is kind of problematic as well, because you have flow splitting, and nobody knows whether your center line is following this flow splitting or not. But here, even in this internal carotid artery without branches, you see here some discontinuity of Walsh stress, which is caused just with the bad alignment of the Walsh stress of the tangential vectors. So, and now on the right hand side, you see the evaluation of this properly aligned tangential vector, kind of projected tangential field. And here we come to OSI, oscillatory shear index, which measures kind of temporal change of the direction and so on. We have two definitions. The first one, OSIL, is based on the longitudinal Walsh stress. And since longitudinal Walsh stress is the scalar value and has a sign opposite or negative, positive, negative, and we do not put any absolute values. So this value can go up to 1. And this classical OSI version here, which takes the norm of the time integral of the shear Walsh stress vector, which is the maximal 1/2. But imagine that the Washer stress vector has opposite side related to the flow. Then this has minus, this is minus, and but in the absolute value this is a plus. So you do not distinguish, you cannot discover this negative Washer stress in this formula. Okay, but with this formula you can discover it, because if you have minus sign over all times, the time interval is here 1 here circle, so you obtain the maximal value 1. So this is the case where on this figure the surfaces are red. So these are the areas of very high oscillatory shear index 1. It means that in these areas there is a static vortex, which is static backflow. Okay, you have static backflow every time you have some or a helical side flow or backflow here. This is this variant. The variant in the middle is the same OSI, longitudinal OSI, but evaluated with generic, with back tangent vector. So we demonstrated the usability of our new method of tangential field generation. And then on the right hand side, you have evaluated this classical OSI, this amplitude-based OSI. And you can, when you compare on the left and on the right, these figures are somehow similar, because the edges of these OSIs are in the big agreement with edges of these red zones. Okay, this is the value of 1/2. It means at these edges we have oscillatory behavior of Washer stress. But you cannot discover this inside here should be also very dangerous zone of negative flow. And now you can see this here. So here is our Washer stress, just filtered out for negative values of longitudinal Washer stress. And you see here the white arrows of the real Washer stress vector. You see this is aligned back as a back flow, and Washer stress is every time aligned with the flow. Okay, so it means the flow is negative there or there, and you see already in each, this is a systolic and diastolic time on both of the, but all time steps, we have some recirculations, some helical flows and so on. And this was also already the first, in the first slide at the small animation at the first slide was also showing it. Okay, so this was on, sorry for that, this was on predicting the Washer stress or dangerous or risking Washer stresses in a human artery. And now I come to the next. I have to look on the time. Okay, sorry, good. Compliance modeling. So the group of Stuttgart, Giorgio Cataneo, Ashkan, they are biomedical engineers, and they have a laboratory, and they made some measurements of the compliance on carotid artery phantom, which was our carotid artery phantom, but somehow simplified. You can see here some phantoms of the carotid artery, internal and external. You do not see some branches, no? So branches have been cut out. The wall was thicker because of construction or fabrication reasons and so on. And they call it molding process, which is a special technology in order to product or fabricate precise vessel phantom with inhomogeneous wall thickness. So this is not 3D printing, okay? Just to, I wanted to highlight that. And they made some compliance measurements. What does it mean? The vessel phantom has been closed. We have some captions here, and they some pumping fluid inside, and the vessel deforms, inflates, and so on. And the same we do numerically. So what we have with different see the vessel walls here, the inflow, and we have no outflows. We have some caps, okay, And then you can see here the state after some simulation. So it is somehow deformed and inflated. So also the volume has changed. Okay. The volume has changed. So the volume has changed, but in one-dimensional case, they made so-called uniaxial tensile test, meaning that they stretch some material with some stress, okay, and then they obtain some deformation, some strain, some just in one direction. And now these are the measured data, and you see here the relation between strain and stress. You see that this is almost linear, especially at the beginning for very less strain. This could be assumed that this is a linear relation coming or going coming or implying this linear stress-strain relation. Stress sigma is linearly related to strain epsilon with some constant, which is called the Young moduli. Okay, and this Young moduli is nothing else, just the slope of this curve. But for these higher stress strains and stresses, we see some deviation of the linear from the linear behavior. The one curve is for silicon, and the second one is for the hydrogel material. They tested two materials. So what we did with this information, we extract the Young moduli as a slope of these curves. And this is the extracted Young moduli, okay? So we see that the Young moduli is changing with the strain in these measurements. And the change was, we see here different behavior for silicon and hydrogel. I should say that this hydrogel, the red curve, is somehow more favorable, and they want to use this hydrogel because good properties. This is transparent. It's a mimicking the real situation. Okay. So we started to model Young moduli as dependent on the strain, just based on this data. Okay. Then the question was how. So we look at the second Piola-Kirchhoff tensor, which is in principally the strain multiplied with some elasticity tensor. Okay, so C. And the strain times epsilon, C times epsilon is the Cauchy stress tensor. And this Cauchy stress tensor had two parts. The first is the deviatoric part, and the second one is the volumetric part. The volumetric part is responsible for volume change, and the first deviatoric part is responsible for shape change, okay, for the deformation. Okay, and so the trace of the strain is included in the volumetric strain, which is some kind of invariance, strain invariance. There are several strain invariants. The first invariant is called shear strain. The second one is the volumetric strain, denoted sometimes AI, I1. This is the volumetric strain. Okay, this is trace of this strain epsilon, and shear strain is some second root of J2, which is called also gamma is condition strain. Like this. So based on this information, we said, okay, in the same relation as the strain is split between deviatoric and volumetric part, we also split the strain metric dependence between shear strain and the volumetric strain. Okay, and we put this new metric, strain metric, into the simulation and model. Here you can see some computed strain epsilon m. So this metric of the strain, kind of combination between deviatoric and volumetric strain. Okay, and you already see that already achieve big values, almost to 50% of the strain. Okay, which means that we are in higher region of the strain, and we are really modeling the nonlinear situation. Okay, and now the results are as follows. Here in this figure, you can see the dependency of the volume. This is on the y-axis, epsilon on this vertical axis is the volume, and on the horizontal axis you have the pressure. So dependently on the pressure, have the volume change of this phantom. And you see here some measured values from the silicon material, and you have seen you can see the numerical evaluation. Two curves. The blue curve is obtained with our strain dependent Young model, so with nonlinear material, and the green one with purely linear elastic model with some average Young moduli. Okay, and okay, what you can observe, we have not perfect, but very good. Our partners from the studio said it's very good result. Even we read some different papers on it. Even using hyperelastic material, they do not get better alignment on better. So these are quite good results, and you can see also how the purely linear elastic is more linear, and our adapted material has this kind of exponential behavior. And what you see here, we evaluated so-called compliance. Compliance is this formula which measures the relative change of the volume over change of the pressure. Okay, kind of the slope of these curves. But this slope is normally measured in the medical literature for the pressures, systolic and diastolic pressures. Okay, or even for these values, 74 and 103 millimeter of mercury. So you can see here two triangles, which is obtaining this side of triangles, this slope, okay? And the values are written in this table. So in this column, we have purely linear elastic material, we have this adapted material with strain-dependent Young model, and we have experimental values, and with our compliance data are somehow between the linear elastic in the good direction to this real or measured. I mean, you have some measurement error here as well. Okay, it was also has been published this year, and now having this information for the volume change in our phantom, which is some kind of artificial situation, we try to translate or to the real situation. In the real situation, the artery is thinner, the walls are thinner. We have a lot of outlets, and the outlets are opened. So we have boundary outlet conditions. So what to do with that? Okay, what to do in order to obtain the same pressure volume behavior in this physically different real situation? Okay, so from the right side to the left side, you do some topological simplification. You cut off these daughters and increase the wall thickness. So you should increase the wall thickness and take the realistic geometry. Okay, this is with this arrow. But decreasing the wall thickness, you need to increase the Young moduli. So it is in this approach that you look for some multiplicative factor between the Young moduli obtained in this situation and the Young moduli, which should be real, and with some optimization strategy we obtained that this factor is almost 3. This optimization strategy was based on the comparing the volume pressure curves, and we wanted to obtain the same volume pressure curve for this situation as well as for this situation. In this case, we need to take 3 times higher Young moduli, but the same dependent on the strain. Okay, and here are the results. On the left-hand side, you have what you have. You have here the deformation of the vessel. You see very low values, almost blue in millimeters, with 0 stress outflow boundary condition, this do nothing boundary condition, which we at the beginning use, but then we went to resistance boundary condition, which is on the right hand side. This is the same simulation, the same model, just a boundary condition has been changed, and now you see that this resistance alpha boundary condition causing this very high inflation, and this inflation is in accordance to these volume pressure curves. So it means with high pressure, we obtain the same high volume change as it has been done in these measurements, or very similar to this. Okay, just the proper boundary condition. And here you see it was the formation. Here you see the what you see the strain. No, not the strain, the Young moduli. So the Young moduli 3 times 0.3 is about 1 megapascal. And now you see the Young moduli dependent on the strain. The same, he is also dependency on the strain, but the strain is very low because the volume change is very low. Here's the volume change very good, very bigger, and then we have a different distribution of the Young moduli along the surface. Okay, so we use really not a constant Young moduli dependent on the strain. Okay, and probably the last thing to this topic, we also evaluated some graphs. On the left-hand side, you see the temporal behavior of the pressure, so pressure varies. The green color or the green curve is for 0 pressure or 0 stress boundary condition even, and here's for the resistance boundary condition. In the case of resistance boundary condition, we even obtain very good agreement with some carotid artery pressure measurement published in this paper. So okay, even just having some very general carotid artery inflow, we obtain very good realistic behavior of the pressure rate in comparison to the pressure, no pressure on the behavior with the 0 boundary condition. And on the right hand side, you see the pressure volume behavior. In the red color is the open vessel, so this realistic vessel with a lot of branches, and in blue color or cyan color, this is the sealed, so closed vessel from these measurements and first numerical simulation with this closed. And you see we have quite good agreement, and what we had is that we obtain high pressures and high volume increase. And you have here at the beginning the simulation with 0 stress boundary condition, and the stress and the pressure is just oscillating in this very small neighborhood of 0. So therefore we were very happy about that. We could reconstruct this realistic behavior of the carotid artery. So to summarize all this result up to now, we have patient-specific artery. We need the central line which give us morphological information in order to construct longitudinal tangents in order to be able to evaluate negative Washer stresses and directional shear metrics of directional shear as longitudinal Washer stress and derive OSI, which allow us to detect all positive complex flow patterns as here, for instance. Then we implemented the resistance boundary condition, which leads to realistic observed flow distribution to the internal and external, regulated by intracranial arteries, but moreover, prescribing this boundary condition, we obtain considerable impact on the inflation of the carotid artery, and we obtain the realistic pressure volume curves even in this open situation. And what also was observable that the Washer stress decreases by applying the resistance boundary, which is somehow logical. Okay, now I should finish. Okay.
Yes, 5 minutes.
I think some 5 minutes more. Okay. So in the scope of this big project, we got 150 patient geometries, and even then with some artificial changes, we obtained 170. So we took the patient and we put some artificial stenosis inside. So we need to simulate a lot of data. How to do it? The first point is geometrical data acquisition was not done from us. The group of Jena made it CTA imaging, geometrical reconstruction, segmentation of the outer arteries, entity detection, interlumen detection, and the plaque detection, center line computation, and stenosis degree computation. It is called a morphological analysis. And then we started with our automated simulation workflow, which made some geometrical prerequisite in preprocessing, which should be made some automatically for each patient, which is topologically very different, standardized numerical simulation template, but automated model setup by import of the morphology based on individual parameters and some post-processing. So you'll see just a part of the database we generated and some steps. I think now I will split the explanation of this because this is not really our work, but you can look at this link. The carotid analyzer tool was developed by the Jena group, which is able to segment but also analyze the morphology. Look at the change of the radius of the vessel, the stenosis degree, and so on and so on. We are using the tool for the segmentation. Also can be applied for different as the carotid arteries of they're developing something for aorta now and so on. Okay, so now I will split it. Here, our automated simulation workflow was split into 3 phases. We have some input. In the input, we need some patient geometry and the center line. Then we do some preprocessing steps, inlet and outlets, cropping, computation of tangential field, longitudinal tangential field is properly aligned, then the definition, 2-dimensional data set and geometric filters, then putting into simulation template. What we need for the simulation template, there are some import of some parameters, simulation parameters, also this tangent field, but also for definition of some filters and some planes which are aligned with individual artery and so on. A lot of work. And in the post-processing, we need to process volume data, surface data, cut plane data, 2-dimensional data, filter data, and so on and so on. That database we have it's open source database for everybody, and all these kind of data are saved there. And this workflow is based on some scripting, this kind of octave script, which is the free version of the MATLAB. So at first we take the center line for each patient. We announce the points of the center line where we want to cut out. Then the programs compute some parameters of them which are needed for definition and templates, setup, and so on. We need a lot of text files in order to import this parameter, this preprocessed parameter to template, to the console template. Then in the console template, for instance, the automatic cropping can be then done automatically just by the import of the parameters, and this has to be done for each patient. And what we also need, sometimes we need some high risky zones as a bifurcation and filter the data. So for this, we need also semi-manually to say what is the beginning and the end of the bifurcation zone at least. And then ellipsoid of neighborhood will be computed, but also not only this, also there's this to singular value decomposition for the cloud point of the bifurcation. We define principal axis for the planes, for cut planes, and for the ellipsoid of neighborhood, and so on. This kind of preprocessing is needed in this automated simulation workflow. Now we have some statistics. So we see that mostly about 1 million or So in our simulation, each of the simulation has different number of elements, but the most simulation it's 1 million elements, and computation time was about 3 hours, and average time was for one simulation was 7.5 hours. You can find our published papers under this link, and this has been also now generalized to almost 150 cases. And for the data usage, just I want to show one data usage with this visual exploration. Our partners from Vienna use this CFD database and these risk descriptors to visualize or to analyze the hemodynamic space on morphology similarity. What this means, we have a database of 150 cases, and the physician takes some current patient segment and then compare, and the carotid analyzer or the extension of carotid analyzer is now able to compute the 10 best matches based on not only the morphological similarity, but also on the stenosis degree, on the radius change. Okay, this is the first one. The second one is machine learning. They did some graphical neural networks in order to classify the patients based on washer stress. They classified the stenosis degree. So here is the very short slope of the extended carotid artery. This is the first carotid analyzer, which has morphological analysis, and then the new functionalities is computing similarity, morphological similarity, and you can then explore your case, not just your case, but the pre-computed very similar case, or 10 cases you see here. So you got 10 cases. This is your current case, and you got 10 cases, and you can explore this on the flatten through cutting and flating of the surface. And you can explore 2 cases or another 2 cases, which you have different similarity measures, so you can switch one of them and so on. Okay, some comparison that our measure, combined similarity measure, which takes into account not only the shape but the diameter profile, so how the diameter change along the center line and the stenosis degree, and in every cases on all these evaluations we could better error than the classical measures. And this is the final slide. I very like this figure, because in this figure you can see that our longitudinal Gaussian test, which is in blue color here, this is the reverse or minus, in minus values, this is the negative longitudinal Gaussian test. You can observe it at the surface, and when you look at the streamlines, you can see this very strong helical flow, which is very pathologic. In comparison, for no negative Gaussian stress case, you have some good aligned flow. So it was like a usage of our approach. So thank you very much for your attention. Now some people who was aligned with this contributed to this. These are my 2 students, Kevin and Tristan. And Kai Lavon is a professor of visualization of visual analysis, and his postdoc, almost postdoc now, and Giorgio Cataneo from the Stuttgart, and his postdoc, who made the measurement. So thank you very much for your attention. Now I'm done.